Hey, welcome back to your favorite calculus class, you guys. This section, we're going to present what's called the fundamental theorem of calculus. Some textbooks will actually call this the fundamental theorem of calculus part 2. We'll just call it the first fundamental theorem of calculus. This is the central theorem in integral calculus, so it connects integration and differentiation, enabling us to compute antiderivatives of the integrand rather than by taking limits of the Riemann sum as we previously did, right? By the way, Leibniz and Newton exploited this relationship, and they started mathematical developments that fueled the scientific revolution for the next 200 years, and that was about 1665 or so. Archimedes was actually pretty close. With a limiting process, had he developed calculus, and boy, he was really close, hundreds of years earlier, who knows where we'd be scientifically at this point. But we also present an integral version of the mean value theorem, which is another important theorem and is of integral calculus. It is used to prove the fundamental theorem. So let's get going here with this fundamental theorem of calculus. So this is saying the integral of f of x dx is the antiderivative evaluated at b minus the antiderivative evaluated at a. Here's another way to say that. So we find the antiderivative from a to b. So we plug in b, subtract, and we plug in a. Okay, that's the fundamental theorem of calculus. So let's look at this first one here. From 1 to 3 of negative 3x squared plus 12x minus 9. You can see it on the right. We're going from an x value of 1 to an x value of 3. You can see that we're finding this area, right? It's all positive there above the x-axis. We're finding the area under that curve there from 1 to 3. So let's go ahead and evaluate this. Let's use our integral rules now, our antiderivative rules. So the negative 3 stays there. X to the 2 plus 1 is a 3 over that same 3, plus constant stays there. X to the 1 plus 1 is 2 over 2 minus 9, and we throw that 1 times the integral of 1, which is x. Right? And this is from 1 to 3. Let me come over here. Notice the 3's cancel. So I got negative x cubed plus 6x squared minus 9x from 1 to 3. And now we're going to throw in the 3. So I got negative 3 cubed plus 6 times 3 squared minus 9 times 3. So the antiderivative evaluated at b minus the antiderivative evaluated at a. Now it's minus the whole thing. Notice I got 3 terms here, so make sure you put that whole thing in parentheses. So I got negative x cubed, I'm plugging 1 in for x, plus 6 times 1 squared minus 9 times 1. All right, and so we've got negative 3 cubed, 3 times 3 times 3, 27. Oops. Plus 6 times 9, so plus 54, minus 27, minus negative 1 is cubed, plus 6 times 1 squared minus 9. So we've got negative 27 plus 54 minus 27, minus, I got negative 1 plus 6 is 5, 5 minus 9 is negative 4, so plus 4, negative 27 minus 27. That's negative 54 plus a 54. Those are gone. Plus a 4. So it looks like this area ends up being 4 units squared. All right. Here we've got the function u minus 1 over u squared. You can see it's graphed there from negative 2 to negative 1. Now notice this is below the x-axis, right? Here's our x-axis, there's our y-axis, this is below it. Here's our function here, right? This is going from -2 to 1. So it's adding up, like it's taking all these rectangles and adding them up. Well, the problem with this is your functional height. Think of your Riemann sum. If it's finding the functional height, the function right here is negative. So it's taking a negative value times its width, which is positive, plus the next rectangle, which has a negative value times its width, which is positive. So it's adding up all these negative values. So this area, the problem is it's a negative value. This integral will be less than 0. So it's not really the area. So the area of this would actually be the absolute value of all that. It would be the absolute value of whatever you get. I'll put this as the integral. Because the integral, which is the same as the Riemann sum, right? The limit as n goes to infinity of that Riemann sum is going to spit out a negative value because all your functional values are negative on this. All right, let's go ahead and run this now that we've addressed that the area is the absolute value of that. And we'll come back to that after we find this value here. So let's run this integral here. It looks like it's in terms of u. So we got u minus, I'm going to write this as u to the -2 du from a u being a -2 to a u being -1. So I can run the power rule. So we've got u to the 1 plus 1 is 2 over the 2 minus u -2 plus 1 is -1 over -1 from -2 to -1. So I've got u squared over 2 minus, and then this is -1 over u, so plus 1 over u, from -2 to -1. So I've got u squared over 2 plus 1 over u, -2, -1. Now I'm going to plug in the -1. So I got -1 squared over 2 plus -1 over u minus, I'm going to plug in the -2. -2 is being squared over 2 plus 1 over -2. So it looks like we've got 1/2 minus, oops, I'm sorry, I did that wrong. That was right here, that's a positive 1 over u. I got to plug the u in. That was a -1 right there. Sorry about that. So minus 1 minus -2 squared is 4 over 2. That's a half. So it looks like I got a half minus 1 minus 4 over 2 minus 1 over 3 over 2. So I got a half minus 3 over 2 is -2 over 2. Still got the -1. So this is -1 minus 1, -2. So the integral ends up being -2. Now, is that the area? No, because it's below the x-axis. As we mentioned, all these functional heights of these rectangles are negative. So it's taking that negative times negative times positive. So it's giving us that this is -2. So the actual area of this black area would be the absolute value of -2. The actual area of that is 2. All right, this next one, I'm going to rewrite it with a common denominator. So we got from 1 to 8, 3x squared is over the 3x squared minus x to the 2/3, right? That's x squared to the 1/3, or x to the 2/3 over 3x squared. Now remember, well, the x squareds are going to cancel. The a to the m over a to the n is a to the m minus n, right? So what we've got here, we've got a 1 to 8 of 3 over 3, which is just a 1, minus 1/3 x to the 2/3 minus 2. So 2/3 minus 6/3 is -4/3 dx. Okay. And now I'm going to run my integral. The integral of 1 is a constant times x minus 1/3 x to the -4/3 plus 1. So negative 4/3 plus 3/3 is negative 1/3 all over negative 1/3, or times by negative 3/1, however you want to think about that, from 1 to 8. All right? And so we've got x plus x to the negative 1/3. All right, I got negative 1/3 over negative 1/3. It's like negative 7 over negative 7, positive 1, from 1 to 8. Or if you want to write that as x plus 1 over the 3rd root of x from 1 to 8. Now let's go ahead and plug in the 8. I got 8 plus 1 over the 3rd root of 8 minus, now I'm going to plug in the 1. 1 plus 1 over the 3rd root of 1. And so we've got 8 plus the 3rd root of 8, or 8 to the 1/3. 3rd root of 8 is 2. Right? I got 2 times 2 times 2 is 8. Minus 1 plus 1 over the 3rd root of 1. And so we've got 8 plus a half minus 1 plus 1 is 2. So I got 6 plus a half. I got 12 over 2 plus 1 over 2. I've got 13 over 2 on that one. Now this one's a little bit tricky. I know we've done absolute value geometrically in the last section, but how do you do it algebraically? Well, if you think about the absolute value of x is x whenever x is greater than or equal to 0, or the opposite of x when x is less than 0, right? That's the absolute value of x. It's x is greater than or equal to 0, or y equals negative x if x is less than 0, right? That's the absolute value definition. It's made up of 2 different lines. So the absolute value of x minus 3 is what we have here. The absolute value of x minus 3 would be x minus 3 whenever x minus 3 is greater than or equal to 0. In other words, x is greater than or equal to 3. Or it is the opposite of x minus 3 whenever x is less than 3 on that, right? And so that's your absolute value of 3, right, made up with those two. Now, the part here that's a little tricky is you've got transformation of it. You flip over that absolute value, and then you bump it up 3. But we can still make this up of 2 different lines. Here's my first line. See how that's the line y equals x? I've got a y-intercept is 0 and a slope of 1. So it's the absolute value of x, and it's going, if you notice, from this x value of 1 up until this value of 3, from 1 to 3. Okay. Now, what's this line over here in red? Well, from 3 on, I can use, right, whenever x is greater than or equal to 3, the absolute value of x minus 3 is just x minus 3. So I could write this as from 3 on, 3 minus, and I could drop the absolute value. Now, if you want to do that a different way, you can, which is, that's just a line. Why don't you use the point 3, 3, and use another point, let's say 5, 1. And you could write the equation of this line. Notice it's 3 minus x plus 3, or 6 minus x, or negative x plus 6 from 3. And we're only going up until an x value of 4 on this. So if you're doing it that way, instead of thinking about it as an absolute value, you have 2 points. So I would find the slope of those 2 points. So you got negative 2 over 2. So you got slope of negative 1. And then use one of the points. Let's use 5, 1. Y minus y1 equals m x minus x1. So y minus 1 is negative x plus 5. Add 1, add 1. You see how you have y equals negative x plus 6? Same thing right there. So however you want to do that, you can use it with the absolute value definition, or you can just take 2 points on that line and write the equation of the line, right? Either way, you get the part from 3 to 4 is on underneath that line, negative x plus 6. Y equals negative x plus 6. Now we can run our integrals here. So the integral of x is x squared over 2 from 1 to 3, plus, now I'm going to run the integral here, negative x to the 1 plus 1, over that same 2 plus constant times x from 3 to 4. Now I'm going to throw the 3 in, 3 squared over 2 minus 1 squared over 2, plus, now I've got negative, plug the 4 in, minus, and I'm going to plug in the 3 now. So we got 9 halves minus 1 half plus negative 16 over 2 plus 24 minus negative 9 halves plus 18. 9 halves minus 1 halves, 8 halves, or 4, plus I got negative 8 plus 24. Let me just distribute that, plus 9 halves minus 18. So I've got 4 minus 8 is negative 4, plus 24 is 20, plus 9 halves minus 18. 20 minus 18 is 2, plus 9 halves, and then 2 plus 9 halves, 4 over 2 plus 9 over 2 is 13 over 2. All right, let's take a look at this next one. We got 1 minus sine squared. Remember, sine squared plus cosine squared equals 1. So 1 minus sine squared is the cosine squared. So I would switch that to the cosine squared over cosine. Oops. Squared is already there. D theta. Well, that's just a 1 d theta from 0 to pi fourths. And now I run the integral of 1 d theta would just be the theta. Right? This is in terms of theta. From 0 to pi fourths. So it looks like I plug the pi fourths in minus, now I plug the 0 in. So we got pi fourths minus 0, which is just pi fourths on that one. On this next one, I'm looking at that 2 minus cosecant squared. I'd go ahead and look up, well, first of all, go ahead and take the integral. So I got 2, constant stays there, times theta, minus, now I look up the integral of the cosecant squared. The integral of the cosecant squared is negative cotangent. And I'm going from pi fourths to pi halves. So I got 2 theta plus cotangent theta from pi fourths to pi halves. So let's go ahead and throw in the pi halves. So I got 2 pi halves plus cotangent pi halves minus, and now I'm going to throw in the pi fourths, 2 times pi fourths plus cotangent pi fourths. So we've got pi, and then cotangent pi halves, that's cosine pi halves, which is 0 over sine of pi halves, which is 1. And then I'm going to distribute that minus 2 pi over 4, so minus pi halves minus cotangent of pi fourths. So that would be cosine of pi fourths, which is root 2 over 2, over sine of pi fourths, which is root 2 over 2. So we got minus 1 right there. So we've got pi plus 0 minus pi halves minus 1. So we got pi minus pi halves is pi halves minus 1 on that one. All right, on this next one here, I'm going to go ahead and You know, I'm going to write that as the integral of 1 over x, 1 to 2, and minus, I'm going to put that constant out front, e to the 2x dx. And the reason is because I'm taking that, it's not the integral of e to the x, it's e to the 2x. So I want to use u substitution, if you remember that from first section. I'm going to let u be 2x, so du dx is 2. Now make sure you take the dx to the other side. So du is 2 dx, right? So I need, in order to have a du in there, I need a 2 dx. So I give it 2 dx. That'll give me a du. But that means I got to offset it with a 1/2 out front. So let's see what we have here. We have the integral of 1 over x dx minus 2 over 2 is just a 1. And then I have a 2e to the 2x dx. Now remember, the 2 dx, that's my du. And then I have e to the 2x. Remember, 2x is my u. So I'm just integrating e to the u du. Right? That's why I did that u substitution on that. And this is x being 1 to x being 2. So let's see what we get. I go ahead and look on, well, you should know the integral of 1 over x is just the natural log of x on that. And we're going from 1 to 2 on that. I should throw an absolute value on that. The integral of 1 over x, the absolute value of the natural log of x. Natural log of the absolute value of x, sorry. Minus, then the integral of, remember the integral of a to the x is 1 over ln of a to the x, right? So it's 1 over ln of e, which is just 1. And then e to the u. Well, the u here, put the u back in. This is also from 1 to 2. So we've got the natural log of the absolute value of x, and they're both from 1 to 2, minus e to the 2x, 1 to 2. So if you want, you can just put them back together. Now we're going to plug the 2 in. So we got natural log of the absolute value of 2 minus e to the 2 times 2 minus natural log of the absolute value of 1 minus e to the 2 times 1. And so we've got natural log of 2 minus e to the 4th minus natural log of 1 is 0 minus e squared. So we've got ln of 2 minus e to the 4th plus e squared. And there's our integral. All right, let's take a look at this next example. Now in this one, I want you to look at your reference sheet, and if you notice, you have on there this formula that the integral of 1 over u square root of u squared minus a squared du is 1 over a, the arc secant of the absolute value of u over a, and then plus c if it's not a definite integral. So in this case, let's look and see if this will fit that pattern. Let me rewrite this as 1. We got x, we got square root. Notice this is 2x quantity squared. So there's our u. That's our u. A is just a value, by the way, a constant being squared here. So in this case, it's 1 being squared dx. Okay, so hopefully you notice that's going to be our u here. And so what we're going to do is we're going to use u substitution, and then we'll apply that integral rule. So let's go ahead and let u be 2x. So du would be 2 dx. All right. So I need a 2 dx in order to put du in. So I'm going to go ahead and give this a 2 right there, which means I got to offset it with a 1/2. Alright, now let's go ahead and look at it now. We've got 2, got a dx. I'm going to actually put that half inside. I'm going to put that half multiplied by that x right there. I'm going to make that a 2x. And the reason is I want that to be u. Anyway, so I'm going to put that part inside, multiply it there. Okay? And then notice I got u squared minus a squared. All right. So there's my du. There's my du. Here's my u squared, and then there's my a. Okay, so we've got 1 over u square root of u squared minus a squared. And so we can say, oh, that becomes 1 over a arc secant of the absolute value of u, which our u is 2x, over a, which is 1. Oops, I should have put my a in over here. That was 1. And then this is from, let's see, we were going from a half to 1 over root 3. That was our a and b, from a half. Remember, this is x being a half to x being 1 over root 3. Okay. So let's go ahead and plug that in. Arc secant of the of 2 times x, and notice that the x's here are both positive, so I'm going to drop that absolute value. So 2 times 1 over root 3 minus arc secant of 2 times the half. And so we've got arc secant of 2 over root 3 minus arc secant of 1. And I go ahead and go to the side. If you remember the arc secant of 2 over root 3, that means the secant, I'll go ahead and go to the side for a minute. Remember from trig, the arc secant of 2 over root 3, I'm going to set equal to theta for a minute. Well, that means then that secant of theta would be 2 over root 3. Now, I'm looking between 0 and pi on this. So, in other words, secant's 1 over cosine pi. So, I'm looking for this answer. Where would the cosine of theta be? Root 3 over 2 between 0 and pi, right? Again, we're involving the arc here, or the inverse secant. That's why we have that restriction. I'm looking from 0 to pi for this. So the answer to that would be pi 6. Theta would be pi 6. So the arc secant of 2 over root 3 is pi 6 minus, and then similarly for the arc secant of 1, that would give you 0, because the secant of theta equals 1. And so cosine of theta would be 1, which means theta would be 0. So this just ends up being pi 6 on that. All right, this next one we're integrating 2 to the x. So I want to use the rule that the integral of a to the x is 1 over ln a to the x, plus a constant, of course, but we have a definite integral here, so we'll plug values in. So we have no issues here, no need for u substitution or anything, so this just becomes 1 over ln of 2 times 2 to the x from -1 to 2. And so we got 1 over ln of 2 times 2. Now I plug the 2 in, minus 1 over ln of 2 times 2 to the -1. And so we got 1 over, or I should say 4 times 1. We got 4 over the ln of 2 minus 2 to the -1 is 1 over 2. So that goes down, minus 1 over 2 the ln of 2. I'm going to go ahead and get a common denominator, so I'm going to give this a 2 times 2, so that both of them have 2 ln of 2 as the denominator. So I got 8 minus 1, which is 7 over 2 ln of 2. All right, on this next one, you want to rewrite this So that you have 1/2 x to the negative 1/2. So you can use the power rule, minus 3x squared. You can use the power rule there as well, from 0 to 1. So this just ends up being 1/2 x to the negative 1/2 plus 1. So that's a positive 1/2 all over 1/2. So all over 1/2. In other words, if you're dividing by a half, you're multiplying by the reciprocal 2 over 1. So times 2 over 1. Minus 3 stays there. X to the 2 plus 1 is 3 all over that 3. And this is from 0 to 1. And notice 1/2 times 2 over 2, that'll cancel. So you're just left with x to the 1/2. So square root of x minus x to the third from 0 to 1. And so you've got square root of 1 minus 1 cubed minus square root of 0 minus 0 cubed. So it looks like we got 1 minus 1 minus 0 minus 0. So we got 1 minus 1, which is 0, minus 0. So this ends up being 0. Now I want you to look at the graph here. When you're going from an x value of being a half, right here, I'm sorry, from 0, x being 0, to here's your x being 1, right? And so it's taking into account this, right, which is a positive amount. This is the part ends up being 1. It's above the x-axis, that area. Now here, remember we said if I'm finding the heights of these rectangles, the heights of them is giving you the functional value with the Riemann sum a formula. And so this gives you the negative of the actual area. So this gives you the negative on that. So, whoops, I'm not even sure that that's 1. Maybe that's a half or so. But either way, this is a negative. Whatever value this is, let me call this x value. This is opposite of that. And so they cancel each other, right? X minus x, when I add them up, x minus x gives you 0. That's why this integral is 0. And again, let's give it a value. Let's say this is 2. This would be the exact opposite, negative 2, because this is symmetric. It looks like you have the same amount of area above it as you do below it. Okay, so when your value goes below the x-axis, the total area, if this area was 2 above and this integral below is negative 2, you want to slap absolute value on this. So the total area would be 2 plus negative 2, or whatever, right? 0. Or, I'm sorry, 4 in this case. In this case, it'd be 2, right? It'd be 1 and negative 1. Let's do another one that's kind of like that. This one goes from 0 to 2 pi. So when it does the integral from 0 to pi on this, this will give us the actual area right there, a positive amount. Let's call it, let's say it's, I don't know, 1, 2 again, right? If I go from pi to 2 pi, it'll be the exact same amount, but it'll give me the negative value of that. Again, that's because all the heights are negative, right? And so if I was actually finding the total area, we'll do that example down below and have that discussion, but I would have to throw absolute values on that and add those up. Okay? Let's go ahead and do it. Let's just find the integral. Hopefully you'll notice that this integral will cancel and end up being 0. So we go ahead and run the integral of the sine, which is negative cosine. We're going to go from 0 to 2 pi. So negative, let's go ahead and throw in the 2 pi minus. Now let's throw in the 0. And so I got negative. The cosine of 2 pi is 1 plus negative times a negative, positive. Cosine of 0 is 1. And so we have negative 1 plus 1, which is 0. Oh man, oops, I wrote 1 on that, 0 on that. Sorry about that. Negative 1 to 1. Now, again, that's not the total area, right? That's not the total area. The total area is, in fact, let's do it separately. Let's go from 0 to pi. If we did the integral of the sine just from 0 to pi, negative cosine 0 to pi, and then we added in the pi to 2 pi, which is what we're doing. I just want you to see this. So negative cosine pi minus negative cosine 0. So negative, now the cosine of pi is negative 1, plus cosine of 0, which is 1, right? And so that ends up being 2. And so that is an area of 2 right there. Okay. Now let's do this. I'm going to do it in red over here. This is going to give us a negative value. So the pi to 2 pi part, it's the integral of the sine is negative cosine. I go from pi to 2 pi, so I got negative cosine of 2 pi minus negative cosine of pi. So I got negative, the cosine at 2 pi is 1, plus the cosine at pi is negative 1. So I got negative 1 plus negative 1 is negative 2. Right? This spits out negative 2 right there. Again, that's not the area. That's just the integral. Right? It's spitting out the integral. The actual area, I would have to slap absolute values on that. So the total area, here's 2. That's the absolute value of negative 2, because the integral gives us negative 2. So that area is 2, so 2 plus 2 is 4, right? 2 plus 2 is 4, and that's how you find your total area on that. So again, we went from 0 to pi, and then we got to slap absolute values when we do the integral from pi to 2 pi. On that. That gave us 2. That gives us negative 2. Add the 2 together. We get our total area being 4 on this. All right, let's do another one here where we're finding total area. So on this one, the first thing I'd want to do, let's say that I didn't have the graph. So the first thing I'd want to do is I'd want to find, where's my zeros? Where does it hit the x-axis, so I can kind of get an idea of where it's above and where it's below the x-axis. As I take an x out, I got x squared minus x minus 2. So I got x minus 2, x plus 1. So x being 0, x being 2, x being negative 1. So here it hits at negative 1, hits at 0, and it hits at an x value of 2. There's all my x-intercepts, right? And now the second thing is, if I'm finding the total area, then it would be from negative 1 to 0 of the function. This is going to give me a positive value. That'll be the area. That'll be fine. Plus, but when I go from 0 to 2, this is going to give me negative. So I got to slap absolute values on this, because it'll give me a negative value, and it already shows there it'll give me a negative 8/3. But let's go ahead and run through it now. So I got x to the 4th over 4 minus x to the 3rd over 3 minus 2x squared over 2 from negative 1 to 0. And so that'll end up being, I got 0 to the 4th over 4 minus 0 cubed over 3 minus 0 squared. So a bunch of zeros minus negative 1 to the 4th over 4 minus negative 1 to the 3rd over 3 minus negative 1 squared. And so I got 0 minus 0 minus 0 minus, and now I got 1/4 minus a negative 1/3, so that's a plus 1/3, minus a negative 1 squared, which is positive 1. Now that'll change all those signs. So I got negative 1/4 minus a third plus 1. So I got negative 3 twelfths minus 4 twelfths plus 12 twelfths. And so this ends up being, the blue part ends up being 5 twelfths. Okay, now let's do the red part over here. So I'll run through this. I got a big plus, but I got to keep that absolute value on that. It's 4 over 4 minus x third over 3. Minus 2x squared over 2 from 0 to 2. So plus, again, keep all those on there. So this will end up being 2 to the 4th over 4 minus 2 to the 3rd over 3 minus 2 squared minus 0 to the 4th over 4 minus 0 cubed over 3 minus 0 squared. So we got 2 to the 4th over 4. So we got absolute value of negative 8/3. So the integral gives us negative 8/3, but we know we're finding total area. So we got to have 8/3. So total area, I take the 5 twelfths, the positive part, plus the absolute value of 8/3. So 5 twelfths plus 8 thirds. Let's get a common denominator, times 4 times 4. And so we've got 5 twelfths plus 32 twelfths. So total area is 37. Oops, that's really bad. 37. I don't know if that's any better, but whatever. 37 twelfths are total area there. This problem here is a good problem I like to use to introduce the second fundamental theorem of calculus, which is also, some textbooks will refer to that as the fundamental theorem of calculus part 1. Just depends on your textbook. But let's go ahead and look at this for a second. If I was taking, see how I have the derivative of this integral, sine theta d theta from 4 to x, right? So I have the derivative. Let's go ahead and run the integral here. The integral of the sine is negative cosine of theta here. And now this is from theta being 4 up to x. And so this ends up being the derivative of, let's keep going with our integral. So negative cosine of, I plug the x in, minus negative cosine, I plug the 4 in. So I have the derivative of negative cosine of x plus the cosine of 4. Okay, so now I'm running the derivative on that. So this ends up being the derivative of negative cosine. Well, the negative stays there, the constant out in front. I take the derivative of the cosine, which is negative sine, plus now I take the derivative of the cosine of 4. Well, that's just a number, right? That's a constant, cosine of 4. So that's just 0. So this just ends up being the sine of x. Okay, so what's my point with this? Well, the derivative will undo the integral, the antiderivative, and it leaves you with the sine. Now, this is, notice this is going from a value up to, in terms of x here. So the x just goes in right there. You can ignore that 4. Because it's taking a derivative constant, if you will. So that's the second fundamental theorem of calculus. That's saying if I take the derivative of an integral, it'll take f, it'll throw g in there. So f of g of x, but if it's not just an x, that g of x part right there, then I got to use chain rule on that. Okay? So that's what's going on. They undo each other, but make sure you apply the chain rule. They undo each other, but you got to apply the chain rule. So here's an example of that. It says find f prime. Well, here's f of x. if I find f prime of x, then I would be running the derivative on this. Which would undo it, which means this goes into all there, and then I run the, well, let's throw that in for t first. So x goes in for t. So I got x squared over x squared plus 1, and then I do run the derivative, chain rule, derivative of x. Well, that's just 1. But I don't want you to forget the chain rule on that, right? So we just got x squared over x squared plus 1. So it undoes it. Let's do it on this one here. So f prime of x would be, now notice I have an x squared up there for my b value. So they undo each other. That goes in for theta, but don't forget you are going to do chain rule on that x squared. Okay? So they'll undo each other. So you'll have sine, you'll have x squared being squared, but then you got to do chain rule on that x squared, take the derivative of x squared, which is 2x. Okay? And so your f prime here ends up being, which undoes the integral, 2x sine of x squared squared, which is x to the 4th. 2x sine of x to the 4th. Average value of a continuous function is our next one here, and that's what this is notating, the average value of a function. So if you're looking at this, like this function that's going all over the place over here in the diagram, I've got this y value, this y, it's got all these y values, right? All these y values. What's the average value of that? Well, you find it with the highlight right there, 1 over b minus a times the integral from a to b. I think a nice way to introduce this is maybe think about, let's say I take, and like I freeze this. Maybe think about this being frozen for just a second. Like maybe it's 3-dimensional, right? And it's being frozen right there in place. Going from A to B, right? It's taking on all those y values on that curve there. If I freeze that, now if it melts, it'll melt, and there's a rectangle whose area is exactly equal to it. So let me try to draw. So if it melts, maybe it melts into this rectangle, and it has the exact same area, right? That rectangle does. And that's what that's saying. And that's at some c, at some c value. So f of c would be the height. So in other words, the area of the rectangle would be f of c times the length, which is b minus a. So f of c times b minus a. That's the area of that rectangle. And we're saying that's equal to this integral from a to b f of x dx. So the average value of that, the y value in other words, the f of c would be, if I divide both sides by b minus a, that right there is the mean value theorem for integrals. In other words, the average functional value of it. That's your average functional value, the average y value along that curve. Okay, maybe that's a way to think about that. Let's look at this one here. You've got negative 3x squared minus 1, and find its average value over the interval. All right, so we're going to use our average value of the function is 1 over b minus a to b, f of x dx. All right, so if you were, if you're plotting this negative 3x squared minus 1, actually, let me blow this up a little bit. Let me make 1 right there. So 0, it's negative 1. Let me make negative 1 right there. So I get 0, negative 1, and then at 1, I'm at negative 4. It's kind of going like this type of deal. Okay, so it takes on all these y values on that curve, right? We're trying to find the average over that curve from 0 to 1. So let's go ahead and run through it. This is our a, that's our b. So 1 over 1 minus 0 from 0 to 1 of negative 3x squared minus 1 dx. So I got 1 over 1, just a 1 out front, 0 to 1, negative 3x squared minus 1 dx. So my average value, if I run the integral here, so I've got negative x cubed minus x, and then I plug in the 0. So we got negative 1 minus 1 minus negative 0 minus 0. So we got negative 2. The average value, the average y value on that interval is an average functional value of negative 2. And that's the mean value theorem for integrals. Thanks so much for watching. I'll see you next time. Thanks for taking notes.